With the 5-axis machining, there's two types of 5-axis machining. We could do indexed, which is also known as 3+2 machining, which we covered in one of the previous webinars. You can go back and review the topics on them. And we can also do simultaneous 5-axis machining. Now, these simultaneous 5-axis machining methods, as I pointed out, is available in our premium configuration. The first step that's involved in any 5-axis setup is to define the machine tool in the machine setup dialog. So as you go into your machining browser, whether you're running RhinoCam or VisualCam for SolidWorks or LibreCam, the workflow would be very similar. So the first step is you go into the machine tool setup dialog, and there's two ways how you can define your machine tool. We could do a manual definition, or we could use load from file, which uses an XML file and has some machine models that are associated to it to represent the machine tool as well. So in the manual methods, we would select the number of axes over here. So for 5-axis, we'll select 5-axis. And then you have the configurations. We currently support 3 different configuration types. Head-head configuration, where the rotation of the 2 rotational axes occurs on the spindle where the part remains stationary on the machine. We have a table head configuration, which is a combination of a rotary table and a rotary head, or a table-table configuration where you have 2 rotary tables, which means the part rotates on the 2 rotational tables and the z-axis remains normal, so there's no rotation on the spindle itself. So to give you a pictorial representation of these, I'm just going to jump back into our slides in here to show you the 3 different configurations I'm referring to here. So the one over here on the left that you're looking at is a head-head configuration, where you can see there's a primary rotational axis and a secondary axis. So the rotation happens on the spindle. So this is typically the case when you have CNC routers or mills where you have larger parts that needs to be machined, and they're basically the parts remain stationary on the bed of the machine. It's its fixture on the machine, and the head can rotate or tilt to get to different orientations to machine the part. So we call this as the head-head configuration. The next configuration is a table head configuration, where you have a rotary table. One of the axes could be a rotational axis, could be on the table. Another one would be a head rotation. So there's just one rotational axis on the head and one on the table. So this would be a table head configuration. And then you have the table-table configuration, where both the rotation is on the table, like a trunnion type of setup, where the part basically is oriented or rotated to different angles depending on the type of operations that you program. So these are the 3 different types of 5-axis machine configurations we currently support in our 5-axis module. And again, folks, if you do have any questions, please feel free to post those questions in the questions panel, and we'll try to get them answered to you. So as we go into the configuration in here, you'll see that there's a choice to select from each of these configuration types. So if we go into a head-head configuration, you would then be able to set your rotational axis. And you'll notice that on a head-head configuration, your primary axis is always defined about the z-axis, or it could be, you could call it a c-axis or whatever it's defined on your machine tool. So the rotation is about the z, and when you select either a positive z or a negative z, you'll see the rotation direction arrow appears on your screen in here. So you can choose, depending on how your machine tool is set up, you can specify positive or negative z for the primary axis. And then the secondary axis could either be defined about the x or the y. So if you actually go into your help system in any of our CAM systems in here, you will notice that for a 5-axis head-head configuration in here, you will see that the primary axis, which is we call it the Z here, and then the secondary is the secondary axis that you see, which rotates about the primary here. So your machine tool could be defined as a C and a B axis. So that C axis or B axis, the axis representation, the code is defined in your post processor. However, you would specify the axis of rotation for the primary and the secondary over here in the machine tool setup dialog. Now, once you establish the primary axis and the secondary axis, you would then also go ahead and specify your rotary axis limits. For the primary axis, it could be no limit, which means the primary axis could go plus or minus infinite in terms of rotation if you do not have any cables or wires that are tangling around to restrict the rotation. Or you could pick from one of these options in here for rotation. It could be plus or minus 360 degrees. You could even set a user-defined limit where you can specify the rotary axis limits for min and max. So for example, on certain machines, it could be -3 to plus 360 degrees, or whatever the rotary axis limits are, these can be set for the primary axis, as well as for the secondary axis, which could be plus or minus 90 or plus or minus 110, or whatever the limits are for your primary and the secondary axis can be set right in here.
I want to jump in here real quickly and explain a little bit more about the secondary axis. You might have a question in your head why the secondary axis is actually moving or rotating about the primary axis. So why do we call it the Y or the X axis? The reason we call it the secondary axis rotation about one of the principal axes, either the X or the Y, is when the machine tool is in the nominal position. That is when we say when the machine tool, all the axes are zeroed out, then we look at the machine tool configuration and say about which global coordinate axis is the head rotating. What is the primary axis rotation about? And the global Z, which is typically called the C axis. And then, and depending on your machine, it's either about the global Y or the global X. So that's how you define the secondary axis. So hope that makes a little bit more sense.
Thank you, Joe. So the next configuration we'll talk about here is the table head configuration. So as you pick the configuration as a table head, you will notice that now the choices for your primary axis can be set to be X, Y, or Z. So your rotary table, the table is defined as the primary axis in a table head configuration. So your rotary table could be rotating along X, similar like a 4-axis setup, what you have, your rotary table, or it could be about Y, or it could be about the Z, the table. Now the picture that you saw in the presentation slide, you will notice that the rotary table in this particular case is about the Z-axis in here, and the head is about the Y-axis for the initial orientation. So in that particular case, I would define the machine tool here as primary as Z, and the secondary would be rotating on the Y. So you would define your primary and the secondary. So if you define the primary about X, then your secondary could be rotating about the Y for the head. So the head could be only X or Y. So depending on how you define the primary axis based on how the machine is set up, you would then define your secondary axis in here. Again, you can set the rotary axis limits for both primary and the secondary axis. Now, the final configuration here we have is the table configuration, where you have 2 rotary tables. So your primary axis again could be rotating on your X, Y, or Z. So if you pick X, then the secondary could be the Y or the Z. If you pick Y as the primary, then the secondary would be X or Z. Or if you select X as your Z as your primary, then the secondary would be the other ones, X or Y. So again, going back to the sample model that I showed in the presentation slide here, you will notice that the primary here could be about the x-axis, and then the secondary is rotating about the z when the primary axis is at the global orientation of 0 degrees. So when the primary at 0, what is the rotation of the secondary axis? That's what you would need to establish in your machine tool setup dialog in here as you define the machine tool. Now, there's one other thing I would also like to point out here is when you set the machine configuration either as a head or a table head, there is the gauge length parameter that you would need to specify for a rotary head. So this gauge length parameter can be set in the machine setup dialog, and the gauge length typically refers to your distance from the pivot point to your spindle face. So as you take a look at any rotary head, you will be able to establish the gauge length, and this information would probably be supplied to you by your machine tool manufacturer, which would be the distance from the pivot point or the point about which the head rotates to the spindle face. And this information, you would be entering it in the machine setup dialog as your gauge length parameter. And then the tool length is defined as you create your tools in the CAM system, whether you're defining. So the tool length could vary because you could be swapping out with different tools. However, the gauge length, the distance from the pivot point to the spindle face, would remain constant for a given head on a machine tool. So the total gauge length is basically defined as the distance from the pivot point to the tool tip. And when you specify a gauge length, a non-zero value for the gauge length in the machine setup dialog, we will automatically compensate for the gauge length in the tool path to account for it, and will be applied or factored in the posted code. So in order to be able to specify a gauge length, you would clear this checkbox in here which says output all coordinates in local setup coordinates, and then specify the gauge length, which is the distance from the pivot point to the spindle face, right in this section in here. So if you set this to 0, in cases where your controller is able to automatically compensate for the gauge length. For example, you could be using something similar to like an RTCP or a G48.1 or a G48S1, where the machine control automatically handles the compensation of the gauge length. And you can set this to 0, and our CAM system will not apply the gauge length compensation. So when this is set to 0, the tool length will not be added in to compensate for the gauge length, and it'll be fully handled at the controller. However, if you'd like the gauge length to be computed to handle by the CAM system in here, you enter the gauge length. So for example, if I put in the gauge length as 9 inches, and you define a tool length of 4 inches, your overall gauge length would be 9 plus 4 would be 13 inches from the pivot point to the tip of the tool. So if you're using different tools, the tool lengths are automatically accounted for in each operation to establish the total gauge length. Again, folks, if you do have any questions, please feel free to post those questions in the questions panel, and we'll do our best to answer them for you. Now, on most machines that involve a head configuration, a combination of head or a table head, you would be post-processing the tool paths by outputting all the coordinates in the world coordinates, which means it'll transform the coordinate values from a rotated or tilted coordinates to the world. And when you clear this checkbox, that's when you can set a gauge length to be output. If you're outputting in the local coordinates, then the gauge length wouldn't be applied, and this option would be automatically disabled to enter in or specify a gauge length. So the gauge length can only be set when you have a configuration that involves a head, rotary head, and when you're outputting it in the world coordinate system. So this is how we can define the machine tool manually using the manual definition process. The other process is using a load from file. So as you select load from file, this will give you an option to select a list of machine tool from the list of machine tools that are included in here. And as you can see, there's a bunch of different machine tools, and you have machine tools right from 3 to 5 axis in here. So for example, if I pick a 5-axis machine tool, I'm going to go ahead and select a 5-axis router in here, and we'll go ahead and take a look at the definition. So as you can see, when you select the 5-axis machine tool, it automatically displays the machine tool model, and it shows each of these linear axes: the primary axis, the x-axis, the z-axis, your c-axis, and your secondary axis is defined about the b-axis. And as you can see right here, you can select each of these, and you can see the rotation here. That's your c-axis, which is your primary axis, as you're noticing it right there. And depending on how you define it in the XML file, you can establish the kinematics for these by setting these parameters in the XML file. And you have your secondary axis right in here, where you can see the rotation of the axis position. So you can define a machine tool using the load from file, and we can help you build a machine tool model. So if you send us the information about your machine tool, and also send us the sample models for each of these axes in here, we can help you put together. And all of these machine tool models can be located in the machines folder in your installed directory. So if you're running RhinoCam, you'll find it in the RhinoCams directory, or it could be in the Visual Cam or Visual Cam for SolidWorks or LibreCam. So we can establish these kinematics, and also the rotary axis limits. All of these parameters can be defined in the XML file. So here you have a 5-axis head-head configuration machine. I'm going to give you an example of a 5-axis table machine, like a trunnion type of machine tool in here. So that's a 5-axis table configuration. Now, if you switch from load from file back to manual definition, you will notice that it automatically sets the machine configuration, the rotary centers, and the rotary axis parameters for the machine tool that you just selected in here. So you could pick from one of these machine tools if the machine tool that you're working on is already listed in here. If it is not, you can use the manual definition option, or you can provide us with your machine tool information and we can help you add this into the list. Again, folks, if you do have any questions at this point, please feel free to go ahead and post those questions in the questions panel, and we'll do our best to answer them for you.
There was a question about are these machine tools available in the professional version? And maybe you can take that today.
Sure, absolutely. So the machine tool load from file option is available right from expert configuration of our product. So to simulate 4-axis, you could simulate 3, 4, and 5-axis. If you have the professional configuration, you could program index 5-axis and define your machine tool in here and use them for machine tool simulation. So the answer is yes, it is available in professional configuration as well. Okay, so the next thing we'll focus on here is how to program 5-axis toolpaths in our CAM system. And to go over this, I'm going to start out with this example in here. This looks like a backrest for a chair, and you can see that there's sculpted surfaces on this particular model in here. And we would like to go ahead and program this particular part using some of our 5-axis continuous or 5-axis simultaneous toolpath methods. So when we say continuous 5-axis or simultaneous 5-axis, what this refers to is you have 3 linear and 2 rotational axes, and all of these axes are moving or changing simultaneously as you're trying to machine along a surface. In the case of indexed machining, you are locking the 2 rotational axes to a given plane and machining them, whereas in the case of simultaneous 5-axis, your 3 linear and the 2 rotational axes are could be changing constantly. So the 5-axis simultaneous methods can be located under the 5-axis methods in the 5-axis menu here, and this is available to you in the premium configuration. And we have different types of 5-axis methods, and we'll try to do our best to cover most of these methods in today's webinar. So we have curve projection machining, flow curve machining, between 2 curve machining, drive curve, surface normal, and swarf machining. So typically, is to start out machining a part like this, you would go through the process of defining your machine tool. So it could be defining as a head, a table head, or a table, depending on the type of machine tool you're working with. And then we'll go through the process of defining the post processor at a later time. And then you'll go through the process of defining your stock geometry. So you could be starting with a rectangular piece of block or whatever the shape of stock it is. And typically for a roughing process, you could be using a 3-axis technique, or you could be using an indexed approach to rough it out. So here I've generated a horizontal roughing toolpath using a 3-axis roughing or Z-level roughing technique. I'm just going to go ahead and quickly run through the simulation for the roughing operation in here. So we have it roughed down as close as possible to the part surface. In the next step, I would like to go back and apply some finishing toolpaths in here. And the first operation I'm going to cover here is surface normal machining. So this would be similar to our parallel finishing that you're familiar with in our 3-axis methods. So we have a method called 5-axis surface normal machining, or also known as surface parallel finishing in 5-axis. So in most 5-axis methods, you would have to pick or select a drive surface. A drive surface is basically the surface on which you want to generate the toolpath to. And as you select a drive surface, you could select one or more drive surface. You can graphically select them from the model. And again, these surfaces could be NURB surfaces. It could be imported as a step file, an IGES file. So they have to be a surface-based model. We'll talk about how to work with mesh models down down the road, in the webinar today. But typically, 5-axis simultaneous machining is performed on surface-based models. So you would select your drive surface, which is the surface that you'd like to machine or program. And as you select the surface and add them to it, so similar to how you select your drive region, you select the surface, and uh, we automatically display the normal orientation for the surfaces that you selected. So you want to make sure that the normal is pointing in the correct direction in here. So if the normals are inverted, then you would need to flip the normals, making sure that you're cutting in the right direction.
I want to just add a little note about these drive surfaces with in 5-axis, what these drive surfaces allow us to do is actually locate not just the cut pattern, which are derived off of either the actual drive surface geometry, but also the tool axis orientations. So we're picking off the orientations of the tool from these drive surfaces. So that defines the orientation of the tool as we are creating the cutter toolpath. So that's why it's important, or it's necessary in the 5-axis toolpath methods to actually pick a drive surface. In 3-axis methods, you did not have to pick a drive surface because there's no tool axis. The tool axis is locked to the z-axis, and so there were some implicit directions we were using. For instance, in parallel finishing, we were either going along X or Y, so we really didn't have it. Really, you can think of it as a planar surface, and we were just driving it along the X and Y of the plane. So, but in 5-axis, we actually have to have a drive surface to define the tool axis. Hope that makes sense.
So would it be okay to say that the tool would remain normal to the surface that's being machined? So when we select the drive surface, since it's established as a tool, the axis normals based on the drive surface that you select. So the tool path you generate would be normal to the tool would remain normal to the surface being machined.
Well, I think it's what we really do internally is we take that tool normal or the surface normal at every point along that tool trajectory from the drive surface. But then later on, the toolpath could be modified using either lead, lag, or tilt angles. So it's not necessary that it's always normal to the surface. But the initial starting point for us for calculations is the surface normal.
Okay. Thank you, Joe. So once we make a selection for the drive surface, you could be selecting one or more of these, and then you make your selection of your tool. So you could be working off with a corner radius tool or a ball mill or even a flat mill. So you make a selection for your tool, and then you establish your feeds and speeds. Now these are very similar to how you've done it in our 3 and 4, 2, 3, and 4 axis, the tool selection, the feeds and speeds. And then as you get into the clearance, in 5-axis, you have more options for clearance definition. Depending on the type of part that you're working on, you could be defining your clearance as just as a plane, similar to how you've done in 3-axis, or you could be using a spherical clearance where you can specify the radius and the center, or you could even use a cylinder clearance definition depending on the axis that you want to pick for the cylinder. It could be X, Y, or Z. So if you have a table head configuration machine and your rotation is on the X axis of your primary, then you can choose a cylinder axis for the clearance. Depending on, again, the type of part you're working on and the machine tool setup that you have, you could pick the clearance definition in here. So on this particular example, I'm just going to go with the planar clearance, and you can set the plane orientation either to be parallel to your setup, parallel to the world coordinates, or you can even put it parallel to an active construction plane that you have set, or you could even pick parallel to a part surface or a planar curve. So you have these different options in here, choices for you to set the orientation for the plane. So once you've established the clearance in the cutting parameters, you have these controls where you can specify the number of axes to output. We'll focus on the 5-axis. We'll talk about the 4-axis output in the later half of this webinar here. You can set your cut tolerance, the stock to leave, angle change, and the distance change. You can choose your cut patterns in here, whether you want to go have the cut pattern run parallel to your X, Y, or parallel to Z. You can pick those options right in here, and you can specify or control your step over. We'll talk about the lead lag angle. So I'm going to go ahead and hit generate to generate the toolpath in here first. And you'll notice that the toolpath is now generated. Your 5-axis surface normal machining, or also known as surface parallel machining toolpath. And I'm going to run a verification or simulation for it, a cut material simulation. We'll select the play button in here. So based on the normal direction we picked for the surface, and you'll notice that the toolpath generated is derived based off the surface normals. And of course, you can control the simulation speed and the accuracy of the simulation as well.
And as you can see, the tool has complete freedom to move in all 3 linear axes, as well as all the two different rotary axes as well.
So I'm going to pause the simulation in here for a moment. We'll switch back to the Program tab. And if you actually take a look at the toolpath editor, you will be able to see the 3 linear axes and the 2 rotational axes, the angles that are being computed for each and every orientation in here. So you can see the 3 linear axes, which are your X, Y, Z, and then your 2 rotational axes in here. Even before you post-process the toolpath, the computed coordinates and the angles are being displayed right in the toolpath editor. So let's go back and take a look at some of the parameters that we have in the 5-axis. This particular operation we created in here, if you go into the information, it shows about close to 66,000 go-to motions that are generated for this toolpath. You could go back and tweak some of these parameters in here. For example, the maximum angle change and the maximum distance change. This would affect the chord segments or the go-to motions. So the smaller the number you put in, you're going to get larger the go-to motions. If I change the distance in here from 0.4 to, let's say, 2 inches, and the angle change, I'm going to change it from 3 degrees to 10 degrees. And when you generate the toolpath, you will notice that this significantly drops the number of go-to motions in here, and we are now down to about a little over 8,000 go-to motions. So what this basically does is it reduces the number of intermediate points, and on machines where you have machines or controllers that have hard difficulty interpreting these finer points, and you might notice some jittery motions on the machine, you can space out these toolpath motions by specifying a larger angle and a distance between points, so you can increase them. So it's not going to affect the quality of your finish, but it's just makes it much more easier for it to work on the machine. So this is one of the controls that you have available.
Yeah, I think I want to also emphasize it really does affect your quality. I'm sorry, Uday, because the number of points, if you increase so the distance between 2 points is basically how far apart the toolpath points are spaced. So you could conceivably make that quite large and actually gouge into your drive surfaces. So that's important to experiment with that value and make sure that you're not compromising the quality of the toolpath at the expense of generating a faster toolpath or having a controller go faster. So it's something that we need to that you as a user need to experiment with to make sure that you're getting the right quality, right trade-off between performance and quality.
Thank you, Joe. So the next parameter we would like to look into is how the tool axis control affects it here. So you have the option to set a lead lag angle as well as a tilt angle. So the lead lag angle is basically allows you to use the leading edge of the tool along your direction of travel. So if I put in a lead angle of, let's say, 15 degrees in here and go back and generate the tool path, so in this particular example here, the lead angle is in the direction of the travel is along the x-axis, so it will allow you to basically use the leading edge of the tool to be able to set it to 15 degrees, so it basically uses the leading edge of the cutter to be able to generate this tool path in here. So this could be one of the way that you can improve the control over the cutting that you're accomplishing here on the surface by using the leading edge of the cutter by specifying a lead lag angle in here. You could also specify a tilt angle, which can be found under the tool axis control. So a tilt angle basically defines the direction which is perpendicular or normal to the direction of travel. So in this particular example, again, if I set a tilt angle in here, you will notice that the tool is basically tilting across from the perpendicular to the direction of travel. So these parameters for tool axis control are available in all of the 5-axis operation types. I'm just going to go over this in one of these operations, and this would work similar in the other operation types as well. Now you also have the option to specify your cut level. So if you want to do multiple passes like a pre-finishing and a finishing pass, you can specify a cut depth control in here. And you can set a depth per cut, so this will create multiple passes. And you can choose the cut traversal between cut levels to be either zigzag or zig. So here you can see there's 2 levels that are being added. You have your first level and then the second level in here. So this could be used as a pre-finishing and a finishing operation. Now the entry and exit tab allows you to set the type of entry motion and exit motions. We have several different types of entry motions in here, starting with tangential arc, vertical tangential arc, horizontal tangential arc, and orthogonal arc, tangential line, orthogonal line. So you can pick the most appropriate entry motion and the exit motion that would be applicable to the surface that you're trying to program or machine. And you can set the sweep angle and the radius for each of these parameters. You can also control the tool axis transition, which could be set to fixed, tangential, or tilted. And this can be set for both entry motions as well as exit motions. Now, one of the very critical parameters in 5-axis machining is being able to set a gouge check. So typically when you program a 5-axis toolpath, you'd be selecting a drive surface or, like I say, a wall surface for machining a given surface. Then you want to make sure that you check for gouge against not only the surface that you're trying to machine, but also check for gouge against adjacent surfaces. So you want to make sure that it doesn't gouge into the adjacent surfaces. And if a gouge is detected, what would you like to do is what you specify under a gouge check strategy in here. So in this particular example, I'm going to go ahead and say add, and I'll pick these radius fillet surfaces in here. And I'm going to apply these two as to the gouge check surface. I would want to make sure that these surfaces are not being gouged as I'm trying to program the top surface in here. So you can specify to perform a gouge check, and you can apply to check against the holder, your shaft, and the tool tip, and you can specify the clearances for the holder and the tool shaft. And you have these two check surfaces selected. So you want to check against your drive surface, which is the surface that you're programming, and check against these two surfaces. And if there's a gouge that's being detected on one of these surfaces, you can apply a strategy whether you want to retract along the tool axis, which means it'll ride along the check surfaces, or you could choose to leave out the gouging point, so it'll exclude those toolpath motions in the areas where it determines a gouge. So you can apply from one of these available different strategies in here and then generate your toolpath. So you could go ahead and pick the strategy, the gouge check strategy that's most appropriate for the part being machined. And this option is again available in all the different 5-axis methods. So this gives you a quick overview of the 5-axis surface normal machining, or also known as surface parallel machining in here. Sure.
Can you talk about the 2 different tool types that we support?
Sure. One moment. In terms of tool types, could you please a little bit elaborate more on what exactly?
No, the different tool configuration, the different tool types that we can support in the 5-axis modules.
Oh, you mean the cutting tool types?
Right.
Okay. So We support ball and mills, flat end mills, or also known as square end mills, corner radius tools. You could have chamfer tools as well as taper tools like tapered ball end mills. Or you can define these are the different tool types that are supported in the simultaneous 5-axis module. And defining your tool, saving the tools to your library works very similar to how you've done in your 2, 3, and 4-axis methods. And if you're using a gauge length, this is where you specify the tool length, which is the distance from the tip to the spindle face. And we add that information to establish the total gauge length for machines that have rotary head and if you're outputting in the world coordinate system. So the next thing I would like to go over here is a few other methods that are offered in our simultaneous 5-axis methods. And we'll cover the swarf machining toolpath method. So in this case, I could consider the swarf machining to be something similar to like a 3D profiling operation in here. So with the swarf machining, you'd be able to select a wall surface, and you can either select a floor curve or a floor surface. So this would basically use like a side of the cutter. So in this particular case, the tool would not be normal to the surface being machined. It would rather, the tool would be, the side of the cutter would remain like parallel to the surface being machined in here. So in this particular example, and I run a simulation, you'll notice that the side of the cutter follows along the surface that's being machined. So this is swarf machining. So you would be selecting a wall surface. In this particular example, the wall surface is the one that I highlighted in here. And you could either be selecting a floor curve or a floor surface if you have one to select for swarf machining. So consider this similar to like a 3D profiling type of method.
And the floor surfaces or floor curves actually restrain the cutter from going below that surface. So you might have that situation where you want to hug a wall, but you don't want to gouge into the bottom surfaces. So that's why we allow you to select the floor surfaces.
I do have an example where I can give you a quick demonstration of how the floor surface works on a swarf machining. So in this particular model here, I would like the tool to follow along the surface but not gouge into this floor surface. So you could be using this as your floor surface in here. So as you run a simulation, you'll notice that this could be used as your floor surface.
So the tool is parallel or hugging that wall, the vertical surface there, and it's riding the bottom blue surface, and that's your floor surface.
The same over here as well, as you're cutting the surface around the bottom of the part. So in the first example, what we looked at here, we used a floor curve. And in the second example that you looked at, we are using a floor surface. So you can specify your wall surface. And again, the direction of the normal is critical. So you want to make sure it's pointing in the intended direction you want to cut. So if the direction of the normal is flipped inward, then you would be cutting on the wrong side. So you want to make sure that you can flip the active normal, or if you have multiple surfaces selected, you can select flip all to flip all the normal directions. And then you can pick between floor surface and floor curve. And you could set the gouge check surfaces too. So similar to how we did the gouge check surface for the 5-axis surface normal machining method. So again, the swarf machining is available under the 5-axis methods, 5-axis swarf machining. Now the next method we'll talk about here is a 5-axis flow curve machining, where we can use this technique to machine the fillet surface, which has the fillet on this model here. So you could use a 5-axis flow curve machining. And in this particular technique, you'll be selecting your drive surface. This could be the surface right in here. And you could pick a drive curve, and I'm going to pick this curve that's on the edge of the surface. So the tool path will basically follow along the drive curve, but then the normals would be derived based off the drive surface that you've selected in here. So it's similar to your curve machining where a long pattern that you're familiar with in like a 3-axis method where you have curve machining and you have the control to where you can set the cut type to along or across. So in this case, you can do along or across in the cut type, and you can specify your step over parameters and specify the tool for it, and then generate the tool path. So that would be a flow curve machining tool path, and tighter the step over, much closer the tool paths are going to be. And again, the normals are derived based on the surface that you select, and the drive curve that you select is used to define the control the cutter locations in here. So as you run a verification, you'll see that it's following along the curve pattern, and the normals are derived from the surface. So this is also known as flow curve machining. And this can also be used in a wide range of applications. So as you specify a rotary axis limits on these 5-axis methods, the computation of the toolpath would automatically apply those rotary axis limits, and you can see those being applied in your posted code as well when you post-process them out to your machine tool. So if I go back in here and I switch to the machine setup dialog and I apply a rotary axis limits in here, when you generate the toolpath, you will notice that the generated toolpath is honoring the rotary axis limits that's being specified in here on the toolpath. So this applies to all of the 5-axis operations. So we could program a 5-axis flow curve machining for the fillet on the bottom as well. The next thing I'm going to cover here is a 5-axis method called curve projection machining. Now these can be used for following on a curve, similar to your engraving or curve machining. And again, the toolpath follows the curve, and the normals are derived from the surface that you select as your drive surface. So you could be selecting one or more curves. You could specify a projection distance in the cut parameters dialog. And of course, you have control for your tool axis where you can set your lead axis, lead lag angle, and also the tilt angle in here. So in this particular example here, the curve projection machining, the curves are projected down to the surface, and the normals are derived from the surface that you pick as your drive surface. So as I run a simulation here, you'll notice that the toolpath is generated on the curves that you pick as your drive curves, and the normals are derived from the surface. So we've covered the 5-axis curve projection machining, the flow curve, the surface normal, and a swarf. We'll take a look at an example where we can program between two curve machining. To go over this, I'm going to go ahead and bring in an example of like a turbine blade model in here. And again, on this particular example, we already have it roughed out using a 3-axis roughing toolpath. Now you could use a machine tool model to simulate this. So you want to make sure that you toggle on the machine tool visibility. And as you select play, I need to make sure that I display the stock geometry in here as well. And as you select play here, it shows your simulation with the machine tool. So here is the roughing process. I'm just going to go ahead and do a pause and simulate to end to skip through the roughing process in here. So we have the stock roughed down to the close shape of the finished part. And then we have programmed a between two curve machining operation. So here I've selected two curves as drive curves in here. These two are my drive curves. Then I have this surface selected as my drive surface. So the toolpath morphs between these two curves, and again the normals are derived based on the drive surface that you've selected in here. So this would be a drive between two curve machining operation in 5-axis. And you have similar controls for your cut parameters, tool axis control, your cut levels if you want to do multiple passes, and you can control your entry and exit and the gouge check parameters. So in this particular example, I've used these two side walls of the blade as the gouge check surfaces. And I've set it to basically leave out the gouging points, as you notice here, so it's not riding along these side walls. And I'm going to run a verification for this. And with the machine tool being displayed, machine tool simulation selected here, you'll be able to see the linear and the rotational axis motions. So you could be programming a combination of different 5-axis toolpath methods, and you could do a combination of both indexed and simultaneous methods as you're programming the part. So over here, we are cleaning up the side of the blades using a swarf machining toolpath. And then I've applied a flow curve machining or follow curve machining toolpath to clean up the top half of the blade section. So you could use a combination of different techniques to program these parts effectively. Now, let's take a look at how we can work with some mesh geometries for programming 5-axis toolpaths. Folks, if you do have any questions, please feel free to post those questions in the questions panel while I try to bring up a file here for going over how to work with meshes in 5-axis. Okay, so what I have here is a mesh geometry. It could be imported as an STL file or one of the mesh formats. You can work with meshes effectively in Rhino and also in our standalone visual CAD/CAM product very effectively. And to be able to program a simultaneous 5-axis toolpath on the mesh geometry, we would actually have to create a drive surface from the mesh. We can't select a mesh as a drive surface since it's not a NURB surface. So we would have to model or extract some curves to create a drive surface from this model in here. So what I've done here in Rhino is I've extracted some section curves from this mesh. So you can use the CAD tools that are available to you in Rhino to extract those curves. And then I've created a surface from those curves. So basically, I offset those curves slightly towards the inside and created a surface from the mesh geometry. You can see that the surface is flowing similar to the mesh surface that you have. And once I have this created in here, I can generate a toolpath for the drive surface. So we can do that by going into 5-axis, and I'll use a between two curve machining in here, and I'll select the two curves. I'll pick this surface edge. I'll go pick this surface edge in here, and then I'll select this as my drive surface. I'll pick a tool. I'll go with a corner radius tool, and then for the cutting parameters, we'll specify the cut. I'll set the angle change to 10 degrees and distance change to 1, and then generate the toolpath. So you'll now notice that if I hide this mesh, the tool axis, the toolpath is generated based on the drive surface that we selected. So the normals are derived based on the surface in here. So it is basically following this drive surface. However, what we are looking to do is we want to machine the mesh surface in here. So I'm going to go back to the program tab and edit the 5-axis between two curve machining operation. And then under gout check, I'm going to select add, and now I can select the mesh geometry as a gout check geometry. So now when I generate the toolpath by setting the gout check strategy to retract along tool axis, you will notice that now the toolpath, the normals are still derived based on the drive surface, but it's following the mesh geometry. So this is how you can program mesh geometries by modeling a drive surface that is slightly offset from your mesh geometry and using the NURB surface that you created as your drive surface for programming 5-axis toolpaths. So as you see here, the generated toolpath is now on the mesh surface. However, the tool axis control is derived from the drive surface that we selected. Folks, as we have a few minutes left here in the webinar, I'll just quickly go over a couple of things in the post processor where you can establish your rotation axis code for your primary and the secondary axis, but we'll be more than happy to help you with your post editing or post processor setup in here. We've developed posts for several different types of 5-axis machines, and to configure the post, if you need help with it, you can always write to us and we'll try to help you to get the post worked out for your machine tool. Typically, the simultaneous 5-axis or the 5-axis setup is done in the multi-axis section of the post processor, and you can define your rotary axis code, the rotation axis code for your primary and the secondary axis under this section, and the macros for linear motion block and the rapid motion blocks are defined over in here in the motion block sections of the post processor. So you're welcome to reach out to us at support@Nexsoft, and we'll be happy to help you, for your post processor settings, and we can certainly help you out with that. At this point, we're open to any questions that you may have in this webinar.
Yeah, there was a question about error conditions. What happens if program position or orientation is unreachable by the machine tool? Maybe I can take that. So if there is something that we compute using the drive surface that the machine tool cannot reach because of the machine tool limits, there's a couple of things we try to do. One is you should understand that for every orientation, there's actually 2 solutions that we can come up with for the rotary axes. So what we would do is we would use the first time around, we will look at the nominal or the closest solution to the previous point. And if that is outside of the machine tool limits, what we check is the secondary solution and see if the secondary solution actually does satisfy the extents or the machine tool limits. And if it does, we will use that. But at the same time, when we use that, we will actually introduce a retract motion to go back up to the clearance geometry and then do the machine tool rotations. Because if we are suddenly switching rotary axes on the surface, you're going to gouge the part. So we actually have to lift the tool up and then perform that rotation to the secondary solution and then come back down to the surface and start machining it. That's something we try, and that works in many cases. But even if the secondary solution is not reachable, then what we do then is we actually error out. We will mark that as an error toolpath, and you will be able to see that in the toolpath editor as an error position. And obviously, you'll have to go back in and try to reprogram that part so that your machine can actually handle machining that type of geometry that you're programming. I hope that helps answer that question.